until I get to very end where I have Zn minus 1 to the An minus 1, Zn, plus in the end I end up with Zn to the An. The special case is when n equals 1, and then this sum is just empty, nothing from 1 to 0, so I just end up with Zn to the An. Okay, so these are my polynomials. And I can think of these polynomials as maps from Cn to C. And there is an isolated singularity at the origin, and there's no other singularity. It's a quasi-homogeneous polynomial. And it's also a tame map in this, and this is, I'm not going to really explain this, but it's what it makes me able to do is that I don't have to take a small ball to define the Milnor fiber. The Milnor fiber is just is just the same. I can just work with the entire fiber, and I can just work with the entire regular fiber of this map PA. So all the fibers except 0 are regular for now, but I'm going to perturb it, so that's going to change later. Okay. So now I mentioned that this is a quasi-homogeneous, so it's good to define this full group of diagonal symmetries up to scaling of this polynomial A. So you have, so let's forget about the last component of the C star to the n plus 1 for now. So lambda 1, lambda 2, lambda 3, lambda n. And these tuples of invertible complex numbers are just acting by diagonal matrices on Cn. And what I'm requiring is that they act in such a way that after I make my action, the overall polynomial gets multiplied by a scalar. Okay, so everyone knows this. It's also called, yeah. So this is the full diagonal symmetry up to scaling group of PA. And I also keep track of that final scaling factor lambda in this group. And the actual group of symmetries is given by this lambda being 1. So those are the ones that actually preserve the polynomial. Okay, and so the way I can think about this is, so I'm thinking about so I have this map PA, and this gamma A acts on Cn by the diagonal action, by diagonal matrices, lambda 1 up to lambda n in the diagonal. And I think of the lambda I action given by just multiplying with lambda on the base, then this map becomes gamma A equivariant. So if I act in Cn by one of these diagonal matrices, then it just rotates and scales the base. I can compensate. That's how I like to think about this. Okay. So now I want to define a dual tuple, which is just obtained by taking the mirror image of the element of my tuple. So it was A1 up to AN, now it's AN to A1. So I just completely reversed the order. So Berglund and Hübsch, this is around 1993. They proposed through some reasoning that, like, every time I give a talk about this subject, I go back and read their paper, thinking that this time I'm gonna really find out, like, well, how they came up with this conjecture, but it never happens. It again didn't happen. But they suggested that these should be mirror models. They have some kind of reasoning. They're physicists. Okay, so that was in 93. In 94, Berglund and Henningson, they gave some kind of non-trivial check. They computed what they call the elliptic genus for these Landau-Ginzburg models, and the check actually checked that they match. And they also clarified this role of the symmetry group, which I mentioned, but I'm not going to get into this this part too much. Okay, and then like around 2007, I think, Takahashi kind of reinterpreted this conjecture as an equivalence of categories, like you do in homological mirror symmetry. Okay, so this is the part where I'm taking a risk. I'm not actually going to define these categories in a careful way, but let me just talk about them a little bit. So this is what's called the Fukaya-Seidel category of this map PA generally. and the objects are Lagrangians. And outside of compact sets, these Lagrangians are supposed to project the radial lines in the base. And these radial lines are not supposed to go in the direction of -infinity. Okay, so that the rays pointing in that direction are not allowed. Anything else is allowed. And if you want to define morphisms, you have to, well, you don't have to, but the version that I use uses this localization trick. So first you define this category where, so you, among this kind of Lagrangians, there's a partial, or there's an order. You can just say one Lagrangian is bigger than the other if it's in the positive direction in relation to the other in terms of just angle. And if you have a collection of Lagrangians in the correct order, then you just define the category as if you just like fix those Lagrangians and define like Fukaya category in the usual way. You have to check some, maximum principle is satisfied, etc. But you just do it like Fukaya style infinity category. But then, if you want to define morphisms in general, then you want to do this thing where you invert some continuation maps. So I will tell you what the consequence of that is. So it has so now if you have like Lagrangians that are not in the correct order, what you're supposed to do is to move them at infinity in such a way that they become in the correct order. I'll show you a picture later on about that. Okay, so any questions, like anything I can say to like make this a little bit more acceptable? Okay, there's going to be pictures. Maybe it will make it more clear later on. Okay, so the category. So this is the A side, and the category on the right-hand side is the stable homotopy category of matrix factorizations. Okay, so this I have no chance of explaining in like 3 sentences like that, but it's some kind. So you have this kind of polynomial obtained by the dual and tuple, and you're looking at kind of chain complexes which are Z-mod 2 periodic, but they're not actually chain complexes. The differential squares to this element. So there I have some kind of module over the polynomial ring, and this module is Z-mod 2 graded, and it's equipped with a module map, but this module map does not square to 0, it squares to this polynomial. And there's also this grading group acting on it. And this is, so the grading just comes from the fact that I have some action on Cn, and I need everything to be equivalent with respect to that action. That you can translate by duality into things being graded. Okay, so now, in particular, this grading group, which is just the, so you take the dual.
Excuse me, Umut. So you're saying, so you look at the matrix factorizations with this polynomial, for this polynomial, and then you have this group acting, and you said that you look at the homotopy.
Yes, yes.
So what is that exactly? So
yeah, so that's the thing. That's this. Whose construction is this? This is a Killen's construction, maybe. It's not an A. It's not the A infinity. It's not what we do with the A infinity categories. It's like you have to form. You have to mod out by injective maps. There's a model structure on this. I think it's better if I don't get into this. It's some kind of. It's in the end computed by computing certain matrix factorizations, and there's some formal procedure. But it's a good question, but I think maybe I will not answer because it won't contribute to this to the talk.
All right.
Yeah. So this the symmetry group up to scaling of the mirror of this of the transposed or inverted tuple. It's dual, it's Pontryagin dual, so the characters on that group act on the right-hand side automatically, okay, just by changing the gradings of the objects that are involved. Okay, And this group, this LA hat, sits in a short exact sequence. And this short exact sequence it has some Z, and then it surjects onto, just the zero part of this symmetry group up to scaling. So just this is the symmetry group, and you can prove that this group is canonically isomorphic to the zero part of gamma A. Okay, so it's every finite group is isomorphic to its Pontryagin dual, but this is a canonical isomorphism. So now something that's a lot easier to understand is this group of symmetries acts on Cn by symplectomorphisms. Okay, these are just some diagonal matrices where each entry is unitary. Each entry is an element of U1. And it also preserves PA, so whatever definition of Fukaya category you use, it should give you a symmetry. But of course, we know that in Fukaya categories, it's not the symplectomorphisms that act, but it's their graded lifts. So graded symplectomorphisms act on it. So for every symplectomorphism, you have kind of this Z many choices of lifting it to an actual automorphism of the Fukaya category. Okay, so by taking graded lifts, you can prove there's something to prove here, that you actually obtain an action of the same group on the Fukaya category. Okay, so now the equivariant version of this conjecture says that this equivalence of Takahashi actually should respect the conjectured equivalent of Takahashi should respect these actions by this group LA hat. Okay, so this is a technical question. So there's all these kind of statements about changing the symmetry group in this story. If there are any experts, and maybe they can tell me, if you prove this equivariant version of the conjecture, would everything be implied by this? There is some way of orbifolding both sides, etc. Let me skip more discussion. But it turns out that you can actually kind of characterize this action in terms of functors that are like not exactly the full action, but most of the action by using operators that are intrinsic to the categories involved. So there is an element in this grading group. So I should stop pointing with my finger. You don't see that. So there's an element of this group F, and that the action of that element corresponds to just shifting by 2. And there's another element of this group, and the mu's power, I will define what this mu of A is, and mu's power of P just corresponds to the Serre functor, the inverse of the Serre functor up to some shifts. Okay, I will not say what Serre functor is again, but it's something that's intrinsic to the category. So if it exists, it's unique. And so using this, you can prove something that I recently realized. So if this coprime condition holds, like if D and mu are coprime, then actually this full action is just generated by a double shift and the Serre functor. So any equivalence actually respects this equivariance. So this equivariance is mathematically, like in terms of information, is only interesting if D and mu, which I didn't define yet, are not coprime. Okay, so mu, what it is that it's the Milnor number of the singularity at the origin of this polynomial. Okay, and that number you can compute. It's this alternating sum. So it starts with the product, and you lose a's from the left. So a1 up to an, a2 up to an, and the signs keep changing, plus, minus.
I just missed something. You said T square and S generate this symmetry group?
If this coprime condition, this condition holds.
Okay.
Okay, so that's mu. D is simple. D is just the product of this positive integers. And I also want to introduce this notation that if I just remove, if I start with A1 up to AN and remove A1, then I will not denote it by this minus A. Okay, that's a tuple. That's a tuple with one less integer. Okay, and then a useful relationship is that mu A plus mu minus A is equal to dA. You can just see that things cancel. And this group that I mentioned in the beginning, gamma A, you can compute that to be just lambda 1 to the dA equals lambda to the mu minus A. Okay, so it's so you can see when these two things are coprime, then this is just a C star. Okay, and then this thing that I mentioned here, this presentation of LA check, which was just the dual of gamma A, it's exactly the same representation that I'm getting. So I just rewrote that basically. It's just the dual group. That's that representation. Okay, so now in order to do my computations on the A side, I will morphify this singularity of PA at the origin, which is very degenerate. We know that its Milnor number is this, so this can be a very large number. And the way to morphify this, at least for my proof to work correctly, is to add a Z1. Okay, so you add the first variable, so you add the variable from the left. And epsilon is any complex number. And again, you can just, for any epsilon, you can just work with the entire fibers. You don't have to do this taking a ball and stuff. And if epsilon is not 0, 0 is a regular value. So it's not, there's not a, the fiber above 0 is a smooth fiber if you actually perturb. And now the point of this perturbation, well, at least one point of this perturbation is that there's a subgroup of this maximal diagonal symmetry group up to scaling, which is of order mu A. It's a cyclic subgroup, and it's given by lambda 1 equals lambda. You can see that for this polynomial, so I want this Z1 plus PA, or epsilon times Z1 plus PA, to be equivalent with respect to this subgroup. So it's going to be some subgroup of the full symmetry group that made it equivalent in the beginning. I turned on some new terms, so this symmetry is going to be broken in some way. It's not the full symmetry group is going to continue to exist, but I want to keep the maximal amount of symmetry. And what this is doing is that this is keeping an order, Milnor number order cyclic subgroup to keep being an action which makes the map equivalent. Okay, but the outcome of this is that, so now I have this mu A subgroup kind of rotating the base. So, and I know that 0 is not a regular value. So if I find one critical value, then I will actually, if I rotate the base by 2 pi over mu A, then I will see another critical value. I will see, because everything is symmetric with respect to this action. So now all of my critical values actually have to lie on some circle, and they have to be equiplaced. Like they have to be equidistant on this circle in terms of angles. Okay? And you can compute exactly what this group is. You just have to put lambda 1 equals lambda here. You will see that it's lambda to the dA minus mu minus A. So that's mu A. It's just lambda to the mu A. Okay. So now one thing that you have to check is that when you turn on this perturbation, the Fukaya category doesn't actually change. Okay, so this is some kind of, you're making a perturbation, and what you have to prove is that nothing kind of fishy happens at infinity, and you can prove that. So all that happens is that I had this degenerate critical point, and it's split into this configuration of mu critical points, which are all placed on a circle. And nothing interesting happens at infinity. They stay the same. And now there was this automorphism of this group given by P. Okay, so I had said that there was this element P. And this element, of course, since these are isomorphic, I can just transfer the action of P onto this perturbed version of the Fukaya-Seidel category. And now I can actually draw you a picture of what it does on objects at least. I mean, I could draw a picture in the unperturbed case, but nothing would move. So the thing that looks like a line in the base would just continue looking like a line in the base. It's just nothing would change in the base. But now that I perturbed, I can actually see the change in the base. So let's say that I have some Lagrangian, which inside the, so these are my equiplaced critical values. There are 5 of them in this example. And some stuff is going on inside, and the rest, it's this radial line. So now I rotate this in the base. So now I have this I have this Lagrangian. Note that these critical points didn't, like they, you know, they rotated, but they look exactly the same because this is a symmetry. So now I obtain a new Lagrangian in the base. It's just this rotated Lagrangian. And then I just bring back the radial line that's going to infinity to where it was by using this kind of root of the monodromy. Okay, so the monodromy would be, you know, the thing that takes a Lagrangian that just goes across this annulus along the black path and turn it into this red guy. And what I do here is I take something that goes like this and I turn it into this guy. Okay, so now I didn't change the Lagrangian at infinity. Well, I changed the Lagrangian, so it's now a different Lagrangian, but it looks the same on the base at infinity. Okay, so now so starting from one Lagrangian, I can just obtain a lot of Lagrangians just by applying this action of P on the base. Okay. So now, okay, so now let's draw this 5 critical values again. So now I know that in order to compute anything, I have to choose this distinguished basis of Tymbals. Okay, so I have to choose a path from each critical point, which goes off to infinity in a, let's say, a fixed direction. And no 2 of these paths are going to be should intersect. So any such collection of paths from critical values to some asymptotic direction is called a distinguished basis. And here my distinguished basis, like the one that I use as my reference distinguished basis, is going to be the one with the blue color. Okay, so there's 5 of them. So this one, I apply this P, I get this one. I apply P again, I get this one. I apply P again, I get this one. I apply P again, I get this one. Okay, so this is going to be my distinguished basis. But now in the proof, I will also need what's called a dual distinguished basis. So the left dual distinguished basis. So those are the yellow ones. Okay, so there's 5 of them. They just they look like this. And the point is that if you want to compute morphisms from the blue ones to yellow ones, you will see that everything is 0. All the morphisms go from the yellow ones to the blue ones. Okay, but what are these purple ones? So the purple ones are what I would obtain if I were to just keep acting by P on this initial Lagrangian that just goes along the positive real axis. I also allow myself to apply inverse of this P. Okay, so it goes you know, in the direction that I was applying P, like this is another one, and then in the other direction this is another one, this is another one, you would have another one. So any 5 adjacent ones of those that you choose are going to give you a distinguished basis of Tymbals, and they're going to lead to the same subcategory of the Fukaya-Seidel category because of the symmetry. Okay. And this whole entire, like if you were to continue generating Tymbals starting from this positive real one and apply P and P inverse, the whole thing, I'm going to call it a geometric helix. Okay, so now I want to kind of, so this Fukaya-Seidel category, this FPA is a huge category. After perturbation, it's still huge. But what's cool is that this kind of distinguished, so this the Lagrangians given by a distinguished collection of paths are supposed to generate this category. So that's finitely many Lagrangians. And if you want to just look at the subcategory given by a distinguished basis of paths, then there are much easier ways to understand that category. So let's go back. And let's just focus on these blue paths or yellow paths, just one of them. So in order to compute that A infinity category, you just keep the order. So the lowest one is the first one, the second lowest one is the second one, etc. And then there's no morphisms going from the higher number to the lower number. And in order to compute the category going from the lower numbers to the higher numbers, you just pick a fiber, regular fiber, right like somewhere here, and just make all of these paths intersect that fiber and each other transversely. And then you will obtain Lagrangians by taking the vanishing cycle on that regular fiber. And then you will just, those are going to be compact Lagrangians. And then you can just do just look at the Fukaya category with those objects. The A infinity category of those objects, but note that I only look at morphisms in one direction. Okay, those are going to be exact Lagrangians. Okay, so now it's supposed to be the case that this, so this is an A infinity category. Now it's computed, it can be computed in the base, and it's directed. Okay, so there's morphisms only going in one direction. And so these thimbles should generate the Fukaya, the original big Fukaya-Seidel category. So this probably follows after some geometric manipulation from what's in Ganatra Pardon Shende. But this is the part that's kind of most not done yet. So I have to understand that this actually is, it follows from GPS. It should, but yeah, this is work in progress. So this is the main obstacle in saying that I completely proved the theorem. Okay, so I had a previous work about this in which I computed the kind of K0 level of this category. So there's something you can do. There's some kind of decategorification that you can do to this category. And obtain with just some vector space with some bilinear form. Bilinear form is computed by looking at some kind of Euler characteristic of morphism, the ranks of morphism groups between different elements. Okay, so that might, if that's not familiar, maybe what's familiar is the ciphered form of this singularity from classical singularity theory. So it's those things are equivalent. They describe the same thing. And what this ciphered form should be, it was conjectured by Orlik and Randall, and I did some computation that checked that what they were conjecturing is actually true. So
I have a dumb question. Doesn't Recursion generate the Fukaya-Seidel category by definition?
No, they don't. Because remember that I put in all these new objects in this category.
Okay.
So there are two kinds of, so the Fukaya-Seidel category started by this definition this guy here was the original definition of the Fukaya-Seidel category. You would choose a distinguished basis and define the category using the distinguished basis in the way that I just described. And then you would prove that it doesn't actually depend on the resulting Ojo category, like the D of the category, doesn't depend on the choice of the distinguished basis. But now there's a second way of defining these categories, which has a lot more objects, but it's still supposed to be generated by this small number of distinguished collections of symbols.
Okay.
Okay. Okay, and if A is the empty tuple, let me just set this A infinity category to be the category with one object and with just the identity morphisms. Okay, just notation. You can think of this as a Fukaya-Seidel category, but let me not do it. So what we will prove is that this category, A sub A, is obtained from the category where I remove the A1 from the left by some purely algebraic recursive procedure. Okay, so this is the way we're going to compute in both sides and prove. Well, so in the end, something that that's strange about the proof, that we won't actually compute the categories. We won't actually give you like generators and relations, but we will say that the resulting categories are the same because they're going to be generated by the same recursion. Okay, very quickly on the B side, so you can, for anyone who already knows what this is, so you can actually, it's explicit what matrix factorizations we use to compute in the B side. So it's this guy. But what I wanted to point out is that the collection that we use, the full exceptional collection that we use in the B side, so the finite number of objects that we use to that we provably computes everything, is also of the same form where you fix an object and just act by this automorphism P to generate new objects. And this type of collection was considered by Aramaki and Takahashi. Okay, and they computed the same K0 level invariant that I computed before me. And their computation and my computation give exactly the same result. They just lead to exactly the same matrices. So this suggests that there should be a mere equivalence taking, you know, my generator Lagrangian to E and P to P. So that let's denote the A infinity category in this case in the B side by B sub A. And we show that the B sub A is obtained by removing something from the other side in exactly the same way, but now you remove from the other side. So that's where this kind of the order change of the tuples come from in the proof. Okay, so let me just quickly run through what this recursion kind of looks like. Again, maybe it will just be impressionistic if you haven't seen it before. How much time do I have?
Close to half an hour.
Okay, great. Okay, so start with any directed A infinity category. So this is just finitely many objects and the morphisms go only in one direction. So now I will explain what this extending a helix means. So you take the triangulated closure of this directed A infinity category, and then there's the exceptional collection kind of canonically extends to an infinite collection of objects in a way that I will describe. And then you just take a longer subsegment of this infinite collection than the exceptional collection that we started with. Okay. And this longer subcollection of the helix is not directed anymore. So there are morphisms, there can be morphisms going in both directions. But we want to keep track of only the morphisms that go in the right direction. Okay, so if there is a morphism that goes in the direction that they weren't supposed to go, looking at the exceptional collection, we remove them. So that defines a new directed A infinity subcategory, a directed A infinity category for me. And finally, I go again to the triangulated closure of this directed A infinity category and consider what's called the right dual exceptional collection. So I take helix, truncate, remove the morphisms that don't go in the right direction, then take the dual collection. And then if the new category is obtained by shifting these new objects of the right dual exceptional collection, then I will say that the new category is obtained from the old one by the recursion R. Okay, so let me try to give a little bit more information about what this is. So if you have any exceptional collection, a triangulated A infinity category, so this means the morphisms just go from left to right. That's the only thing that this means, and something about the self-morphism. If you have any such collection of objects, then you can act on them by some operation that's called mutation. And that just takes two adjacent ones and, for example, moves the one on the left to the right and does something to the one on the right. Okay, it applies what's called the twist of one along the other. It's an algebraic procedure. So this way you can act on your exceptional collections. And given a full exceptional collection, full means full means that all the objects in my triangulated A infinity category can be obtained from this collection by taking cones, shifts. So it's like all the information is contained in this exceptional collection. Yeah, and then, so starting from this, I can extend it to a collection of n+1 objects by just moving the rightmost object here all the way to the left. And move this, the one that it moved over stays the same, the one that it moved over stays the same, it comes all the way here. So, and then it becomes this object. So now I added one more object here. And if you look at now the leftmost n of these objects, again, I get a full exceptional collection because it's some particular sequence of mutations that I applied. And then you can do exactly the same thing to those n things and extend by one more, etc. Okay, and you can do the same thing towards the right, but now you have to use right mutations. Okay. So now what you can show is that if you look at you know, this, now we have this infinite collection of objects, and if you look at the n previous, like so en, I have something new here, let's call it E0. The relation of E0 and En are that they're given by applying the ser functor to 1, and you also again have to apply some shifts. Okay, so let me, in case, so probably the best thing I can say about ser functor is that in the Fukaya-Seidel category, ser functor is supposed to correspond to monodromy. It's not supposed to, it corresponds to monodromy. This is a provable statement. Okay, so if you have some, you know, if you have a Lagrangian and if you apply the monodromy to that Lagrangian, you can extend that to automorphism of the Fukaya-Seidel category, and that is the ser functor up to shift. And the left and right dual exceptional collections, they're obtained by, so you start with this guy and move E2 to the left of E1, E3 all the way from E1 and this new object to the leftmost position, then E4 to the leftmost position. You change the order in that full way of this exceptional collection, then you get the right dual collection. And if you do it in the other way, you get the left dual exceptional collection. And these are dual in the sense that there's morphisms from one collection to the other collection only to the right, only when you know, the new collection is to the right of this home space or to the left of this home space. So they're kind of half orthogonal. And if you wanted to determine the A infinity subcategories with these objects, so like the objects with the left dual exceptional collection or just with objects with the helix, the initial A infinity subcategory, the A infinity category of this exceptional collection determines everything, because everything else is given by some explicit cone. Okay, so the main theorem that we prove is that, so in both sides you start with the same category. It's just a category with one object and one-dimensional endomorphisms, and you know, it's identity, and there's no other higher products or anything. Okay, so the first theorem is what I already mentioned. So this you can obtain BA from BA minus by this procedure R. And note that there's some choice in this procedure R where I have to choose the initial subsegment, the length of the initial subsegment of the helix. So that's something I can change. And in this side, the shifts can be computed. I don't know if I could compute them, but Polishuk can compute them. So it's, and on the B side, on the A side, sorry, this can be proved, but only up to undetermined shifts. So I can't really prove the shift. I can't really figure out what the shifts are. And I put this star because of this Thimble's generate property mainly. So it's almost there. Okay, so this would prove Takahashi's conjecture because we start with the same guys, and you know, all the categories on both sides are obtained by exactly applying the same iteration of the same recursive procedure to the same categories. So up to shifts. So they're not, you won't get exactly the same categories because of this up to shifts business, but you will get the same D of those categories. And the equivalent version in this interesting case, it seems to need a bit more work, but I don't know if anyone cares. Okay, so now I want to explain how we prove the recursion, that the recursion holds in the A side. Okay, so now, so let's start here. So now I told you that, so I wanted to compute the small Foucault-Seidel category of the blue distinguished basis. So instead of doing that, I will compute the small Foucault-Seidel category of the dual distinguished basis, which was given by these yellow paths. But the yellow paths originally went from here to here, sorry, here to here, here to here, here to here, here to here, and here to here. Okay? But now, I could just intersect them at a single fiber and compute inside that fiber. What I want to do instead is I want to move that fiber all the way to the center, to the origin, and carry along all the paths that, all the yellow paths that came with it. So now they look like this. Okay, so I want to compute the vanishing cycles of the first one, second one, third one, all of them inside this fiber, and compute the Foucault category with those objects, but only computing homes from one direction, in the increasing direction. Okay, but it turns out to be better not to compute exactly in this one, but to compute after also you slightly turn on another perturbation, which is this S times Z2. Okay, so an S will be a small positive real number. So without the S, if you ignore the S and set R equals 1, you will get the fiber about the origin of this perturbed polynomial. So just Z1. So up to signs. Let's ignore the signs for now. Z1 plus this guy plus this guy. So Z1 to the A1 Z2 plus P minus A is just PA by definition. So this is just Z1 plus PA equals 0. So that would be just the fiber above the origin. But now I perturbed it a little bit by S. So I added this guy. And I just put this R dependence because I will use it later. For now, it's just 1. And I did these sign changes so that I keep getting critical values at the positive real axis, which is helpful for orienting oneself. So you first want to compute the positive real one and then use that. It's not essential, it's just for convenience. Okay, so now let me tell you what how the vanishing cycles look like as matching paths with respect to this left chest vibration. So this FSR is a left chest vibration for I think actually all values of S and R, but in particular for these ones. And this left chest vibration has two kinds of critical values. One critical values kind of are small critical values, which are here, and there are also big critical values. So they're in these two groups. They look roughly like this. Okay, so I'm not drawing exact pictures. They look roughly like this. I mean, you can prove, I will tell you that there's rigorous proofs of these statements, but pictorially, they more or less look like this. Of course, you figure out all of this stuff by first computing everything in Mathematica, and then you prove what you see. So it's kind of, I'm giving you the Mathematica version here. Yeah, so, okay, so let me just explain now. So if you look at the fifth one here, the one on the positive real axis, that's this simple one. So there's going to be two critical values that are actually on the positive real axis. And you will take the matching path that goes from, one of them to the other. So that's gonna, so if you run this critical value, so there's this vibration. Oh, maybe I actually never said this. So I have this fiber and I use the vibration that I use to analyze it, the left chest vibration, is just projection to Z1 coordinates. Okay, so this is the base of that vibration. Left chest vibration, so they're singular. Yeah, so if you use this kind of Lefschetz bifibration technique, where you kind of use this projection to Z1 for all of these fibers. And you move this regular point slowly to the critical point. What you will see is that these two guys will come together. But this can actually be proven rigorously because everything is real. This is a polynomial with real coefficients. These things are coming together in the real axis. That's why it's easier to prove this one. Okay? Everything is kind of about real polynomials. So this, okay, so let me not say more about that. So you can explicitly compute that the vanishing cycle of this one is this guy. And then the rest of them, what's going on with the rest of them? So now I make these kind of dents along the circle that kind of separates the bigger and the big and small critical values. And now, so what's going to happen for the second one is it's going to rotate. So one end is going to rotate clockwise, and it will come to the slightly higher dent. And outside, it will rotate counterclockwise. Okay. And if I look at the other one, again, it rotates clockwise by 1. So I have this guy. And then it rotates counterclockwise by 1, and I have this guy. Okay, and then I didn't fully draw the first and the second ones, but you can, so then I'm back to the critical value that I had used for the fifth one. So I make a full circle and come all the way up to this guy, and then come all the way to here. Okay, so these are these are matching paths, and their matching cycles are Hamiltonian isotopic to the vanishing cycles here. Okay. Any questions? Okay, so let me say a little bit more about how you get that picture. So, well, so this one I actually didn't figure out in Mathematica. This one I figured out using my previous Mathematica computation, and then some very roundabout way, but then it got simpler and simpler. So I didn't exactly like run something in the computer and this came out. This actually doesn't directly use the Lefschetz bifibration method. You don't just do this thing where you kind of take the regular point to the critical point and watch what happens. If you do that, you get some slightly different configuration, which is okay because there can be multiple matching cycles that represent the same Lagrangian in the total space. That's okay. That's a common phenomenon. Okay, so let's say we dealt with the positive real critical values vanishing cycle. For all the other ones, so I had picked S to be this small positive real number. If I choose S with some special argument, then it turns out that I can compute the vanishing cycle with the critical value of that argument by exactly the same method. Okay, so now I'm perturbing in a different way. So these will move just slightly. They will stay more or less where they are. And now I turn on S not in the small positive real direction, but in roughly this direction. Okay, roughly in the direction of unperturbed fourth polynomial, fourth critical value. Okay, and then you will see that it will be easy to compute. Again, you use the Z1 map to see, and it will be easy to compute the vanishing cycle of this guy in that version of the Millman fiber. And for each of them, you can compute it with different S's. And then what you're going to do is you're going to kind of rotate those S's back to the real axis. And again, watch what the critical values do, and that's how you get this picture. And the point is that as S rotates, so as I kind of look at this picture and rotate S, what I see is that the outer critical values don't move that much, but the inner ones rotate. Kind of as S rotates, the inner critical values rotate with a different speed, but just uniformly rotate. There's some kind of conversion factor, how fast the S rotates and how fast these guys rotate. And that with this observation that I made gives this result. And all of these things that, something doesn't move much or looks roughly like that, it's proved using this Rouché's theorem. I learned this from some strange paper, how you can do this, but it seems actually useful. Well, it was useful here. I don't know how general the technique is. Okay, so, and then finally, what we do is that now we introduce this R parameter, okay? And now we let the R approach to 0. And when that happens, what you see is that these critical values go off to infinity, roughly radially like this. And the inner ones might scale a little bit, but they look roughly like this. They continue looking roughly like this. Okay, but so when R is actually equal to 0, though, what you see is that something strange happens there. So when R is equal to 0, these critical values actually disappeared. Okay, they're not there anymore. And so you set this R equals 0. And now what you're seeing is Z1 equals SZ2 plus P minus A. So exactly the perturbation that I would have used in the previous dimension. The graph, I'm taking the graph of that and projecting with Z1. So that's exactly the same thing as just starting with Cn minus 1 and projecting with the polynomial. Okay, so what I'm seeing, so what I'm seeing in the very end, I will show you another picture. Okay, so now let's go back. So now,
Dumb question again. So
I don't know if it's going to be dumb.
So if you take a full rotation of S, I think we are pushing it into complex numbers. Does it correspond to some symmetry or?
Yeah, so so here, if you rotate the S by a full amount, these guys also rotate. And they will come back to themselves, but after rotating, like not just once, but many times.
And so is this one of the symmetries that you were talking about previously, or?
It's related, but not exactly.
If I'm confusing something.
No, it's not. You're not exactly. So the answer is not exact. So that actually, let me also point one more thing about that. Is that when you do that, when S makes a full circle, these rotate and kind of look the same at the end of that homotopy, but their places change too. So the first one might have become the second one might have become the third one. And that's what generates this kind of non-uniqueness of the matching cycles. Because the family over the S-plane is, if you look at the total spaces, it's a smooth family. So this monodromy that you're seeing, this braid monodromy that you're seeing, is actually, if you look at the total spaces, it's Hamiltonian isotopic to identity. But it's kind of, it's some artifact of the fact that we're using the braid monodromy, a braid parallel transport to analyze this. That's why you would see a different picture if you just applied left chest by vibration technique directly. Okay, so to just sum up what I said is, so we wanted to compute the blue ones in a fiber. Okay, we decided to compute the yellow ones instead. So that will be this kind of taking dual step in the recursive procedure R. Okay, so that's what this corresponds to that. And then in order to compute the yellow ones in terms of the data from previous dimension, I moved this fiber that I'm computing into the origin. And then I computed these vanishing cycles as matching paths. And then I realized that when I send this R to 0, all of these guys will disappear. And the picture that I get here is actually part of the helix. But it's moved. So this would be a part of the helix. Okay, so 5, now I'm acting by the inverse of P. And I'm getting, 5, 4, 3, 2, 1. Okay, so these are all generated by P inverse. But then if I actually wanted to compute the infinity subcategory with these objects and in this only caring about the things in this order, what I would need to do to compute in this category is to actually maximally move them And then I can do Fukuyama's style, just A infinity category, just pseudo-holomorphic polygon counting. Okay, and that's exactly what I see here. So like what I'm computing in this fiber ends up being exactly the same thing as what this helix the subcategory corresponding to this part of the helix is computing. And that's the step where you take the helix and look at the subcollection. Okay, and here to kind of psychologically help you with thinking that it's okay that these things go to infinity and that there's no problem, I think the easiest thing to imagine is that there's an open mapping principle. So I can use an integrable J here. So all the intersections of these Lagranges actually happen inside this yellow circle. And if I want to compute the A infinity structures, with generators coming from these intersection points, none of those will actually go outside of this yellow circle. And this is a result that you can prove using the open mapping principle. There's no intersections outside. Something that left here, it would have to kind of leave and like kind of come back. That's not something that a holomorphic curve can do. Okay, so the recursion in the B side, maybe I'll just skip this. So we use the variation of GIT machinery developed by Ballard, Favero, Katsarkov. So the kind of the key starting point is to relate the category. So this category, so the category of PA minus and the PA. So in kind of the symplectic side, we have this kind of deformations, and as you deform, some critical values disappear. That corresponds to some kind of embedding of one category into the other. So that's much harder to do on the B side. On the B side, kind of you have to come up with a way of relating these matrix factorizations with matrix factorization categories in different number of variables, and that's what you do with this VGIT. I have a reference to it if you're interested and didn't know about it already at the end. Okay, I just wanted to remark on what these categories look like for small n, this A sub A's. And that's going to be my last slide. So we start with this A empty tuple, and that's just one object with identity morphisms. And then you apply R, this recursive procedure. And what you get is this category with Milnor number many objects. And between each edge, and then you put them in linear order, and there's a morphism between adjacent ones in degree 1, and they square to 0. Okay. If you look at the second one, if you apply the recursion again, what you get is again, there's Milnor number many objects. Again, I put them in linear order. Now there's the morphism going between the adjacent ones is in degree 0. And now it actually squares to, it doesn't square to 0, but it's still nilpotent. It still becomes 0 after multiplying with itself A2 times. And these are interesting, but the kind of probably the more interesting thing starts happening in dimension 3. And if you apply it again, now again you will have this x part. It's the same as it's the same kind of shape as the one from A equals A1. So just squares to 0 and degree 1. But now there's another generator. There's another morphism, and this morphism goes between some number of times. So it's exactly A1 minus 1 objects to the right. And this one also is nilpotent with some order. But now the interesting thing is that this y is actually the A infinity is obtained by applying this there is a non-trivial A infinity operation in A1 minus 1, and if you put in x to all the slots, you're supposed to obtain this y. And the conjecture, which I don't know if it's an interesting conjecture or not, but some just just from observations, it seems to be the case that this endomorphism algebra of this category is just kind of as a vector space, just generated by, you take this x's, just this kind of this morphism going between successive elements, and there are some non-trivial A infinity operations. So you just put in this element x in A infinity operations and in nested, iterated ways, in all ways you can. And those elements should give you, should generate the algebra as a vector space. But of course, another possible complication, which I think actually happens, is that you might obtain the same element in different ways. Like you might be able to put x's in some combination of these A infinity product in two different ways, which leads to the same element. So I think that also starts happening when n is equal to 4. So like here, for example, you have x, and all the other morphisms are just, there's only y, and y is obtained by, you take this non-trivial A infinity structure, A infinity product, and input x only. Okay. I think that's all I had to say. So if there are some references to the stuff that I mentioned. The last page.
Thank you very much. So, thank you. Ask some, like, before that, are there any questions?
So, I have a question. There's something I didn't quite understand. This recursion R.
Mm-hmm.
So yeah, so I guess I'm not sure how you deduce the HMS statement from the recursion, because one of the recursion is truncating on the left and the other one is truncating on the right.
Mm-hmm.
So how does, yeah, I guess I just don't see the inductive argument.
Well, so let's say we wanted to prove that the categories for 3, 5 and 5, 3 are the same.
Oh, so the claim is because on the mirror side it's already flipped, so it's actually the same recursion. Okay, thanks.
Maybe I have a question. So you mentioned this conjecture by Orlik and Randall, which you solved, and which is it's probably a classical problem, meaning a solution does not involve symplectic topology, right?
No.
But how it's related? Can you explain, please, how it's related to your story? Kind of?
Yeah. So this Fukaya category, the category itself depends on the well, it doesn't really depend on the symplectic structure, but it depends on some kind of quantum holomorphic disks and stuff, right? But if you do this, so to any triangulated category, you can apply an operation which just gives you a vector space with some non-symmetric, well, it could be symmetric too. It just gives you some vector space with some bilinear pairing. What you do is you take all the exact sequence, like if you have an exact sequence, you say that the central element in the exact sequence, or distinguished triangle, maybe better to say, the central element is the same as the sum of the first one and the third one. And this is just a vector space, and then you also use the Euler characteristic of X groups to define this bilinear pairing. And this doesn't depend on the symplectic structure. It's kind of like the intersection theory. So if you look at the Floer homology between two Lagrangians, that depends on the symplectic structure. But if you take the Euler characteristic of the ranks, then that's just the intersection number of these two Lagrangians. So that's a homological invariant. So that's, I think, the basic answer.
I see. And another question, so maybe related. So what is remarkable in this class of polynomials which you are considering?
Well, yeah, so I mean, I don't know if you, well, to me, it's remarkable because they're very simple and they lead to very nice geometry, and that's somehow, I like working with these objects. So to me, that was enough. But I think the reason why other people might care about is the homological mirror symmetry conjecture. And this homological mirror symmetry conjecture is more general than chain type polynomials. It's about what's called these invertible polynomials. So the invertible polynomials are polynomials in n variables, and there are n terms in these polynomials. So you can describe a polynomial by just a matrix. And this matrix, if it satisfies some properties, then the singularity that you get at the origin becomes non-degenerate. Sorry, isolated. Isolated. Not non-degenerate. It's a degenerate singularity, but it's isolated. And in those cases, you can take this matrix and you can take the transpose of this matrix and define a dual polynomial. And the same story that I talked about today should hold for that class as well. But actually, to be honest, this sounds a lot more general, but it's not actually that much more general. You can prove that any such kind of invertible polynomial with this isolated singularity at the origin condition is actually a sum of this sum in different variables of this kind of polynomials, chain type polynomials, and what's called the loop type polynomials. And the loop type polynomials all are just like this one was a chain, and in the end, the last variable didn't connect back to x1. There it connects back to x1. So you add a x1 to the last term. And actually all this invertible polynomial, all these invertible polynomials are just Tom Sebastiani sums of chain type and loop type polynomials. And like this would be 1/2 of that conjecture up to this business with the symmetry group. So this conjecture also you also have to fix some subgroup of the full symmetry group, and that also has a dual. And there is supposed to be a statement that takes into account also these different choices of the group. So this corresponds to just the trivial choices of the groups on both sides. On one side, you take the whole group, and the other side, you take the trivial group. Something like that. I mean, I don't know if this is, it just seems very strange that this kind of completely naive operation should give you mirror symmetry.
So would your method work also for loop polynomials, or is it known, or what is known?
I don't know. I'm still trying to. It's not going to work exactly in the same way. That's for sure. I have to do something because it really uses this kind of the fact that x1 doesn't connect back.
Mm-hmm.
I use this perturbation, and then I use that kind of to do this induction.
Okay.
If x were to go back to x, it wouldn't work. I mean, something similar should work, but I don't know if it. I don't know how related it will be. You can.
But do I understand well, or you prove that the two objects A and B side are isomorphic by basically computing both of them?
Yeah, that's true.
Is
not
there...
computing them, but so the terrible thing about this proof is that the computations are done entirely separately.
Yes, so there's no connection. There's no connection. I mean, from the A and B side, even though someone still guessed that what the B side is and what I mean.
Yeah. So I mean, I think there might be other.
So the guess that does not materialize into some mathematical, into some ingredient of the proof somehow.
I don't know if I understood. Can you?
I mean, someone guessed that you have a polynomial, not loop polynomials, but the other ones. And then you have they tell you what the mirror should be.
Uh-huh.
The guy who devised, who figured that out, he probably had some intuition on why this happens.
Yeah, so that's why I had this rant in the beginning about every time.
Yes.
Yeah. So I don't. I think they had some intuition. I think from what they write, the intuition that they had is that the one thing that I can. Well, first of all, one thing that's not an intuition, which is that there's this thing called Arnold's strange duality.
Mm-hmm.
And this explains that duality. I think this is one reason to believe that it has something So like everything that appears in Arnold's strange duality can actually be represented by polynomials which are invertible.
Mhm.
And you know, the transposition of these invertible polynomials actually corresponds to the duality in Arnold's strange duality. Like, so this is some, I think this is one check. I don't know if the original paper does this.
But none of these ideas
They do
appear
it
in
for
the
two
proof.
polynomials, huh?
But none of these ideas appear in the play a role in the proof, if I understand well.
But what is the idea? I just don't see the idea here. This is the idea.
Well,
So I think the one idea that they had was that the symmetry group was the same on both sides.
Okay, but many objects have the same symmetry group without.
Yeah, I know, but that's what they said. I don't know. And we use that.
Okay, no, okay. Sorry, I don't want to.
No, I mean, I asked the same
time.
question, but I just don't know. I think there's some other. There was one talk that I listened to by, I think, Jack Smith, where he claimed that he had some way of putting this mirror symmetry into some more general context. But this is definitely not how they came up with this conjecture. You can look at the paper, there's a link to it. And if you figure out how they came up with this conjecture in a geometrically meaningful way, I would be really happy to
sure.
hear. I mean, I don't know.
Okay.
I mean, I had like the B side didn't help me almost at all, I should say. I mean, the only way it helped me is that since the computations seem to match, that's nice. Like they match, so you become happy for a couple of days, and then you go back to just computing. And I don't know. I mean, it's not great, but yeah.
No. That was not my. That's not my.
Can I ask? So maybe it's easier to prove generation by just GPS, but wasn't there a statement like automatic split generation when you have a smooth subcategory?
But is this is smooth?
This A small subcategory A isn't smooth?
Is it?
It's not.
I mean, I don't know how you would. I think it's. So if you like, there is this Orlov's theorem that relates the matrix, graded matrix factorization category with some actual derived category of coherent sheaves of something. But that something is an orbifold, I think. So I don't know. If it's smooth, I don't know that it's smooth.
I don't know. There were theorems like maybe Dikarov, I can't remember. But
I mean, I just didn't think about this.
But no, I mean, like I was talking about the A side.
Yeah.
I'm not sure by some.
You're saying that in general, any Fukaya-Seidel category is smooth?
No, I'm not saying anything.
I don't think this is true.
It's a question, but yeah.
Yeah, I don't know. It's possible that this is smooth somehow. I don't know. You can't construct a good answer there.